Hello Year 11 and welcome to our third video here on calculus. So we've got a bit of a mixed bag here today. We're going to start with a different type of notation we're going to call Leibnitz notation. We're also going to look at an example, a fairly lengthy example with tangents and normals. So what do we mean by Leibniz notation? We've been using this Lagrange notation up until now for functions. So the f of x and the f prime x for the derivative. Now that's pretty good. It's pretty short and easy. It's nice to show your substitutions, right? Because you can replace the x in that notation with what you're substituting in. That's pretty good. But sometimes we've got a few different variables perhaps, or something else going on that we're going to get to later on with things like the chain rule, then Leibniz notation can be a bit more clear, make it a bit easier to understand what we're doing. And it's written like this, dy on dx. Right? That's how it's pronounced or voiced. The d's can't cancel or anything like that. The d's aren't a variable. They just indicate. Perhaps you could think of it as the change in y over a change in x. That's sort of roughly what it is. And you know, that's the gradient, right? Rise over run. The difference in y over the difference in x. It's a little bit like that. You can understand it a bit like that. So it's not a constant, it's not a variable. You can't cancel it. It's not really a fraction. However, we sometimes get away with treating it a little bit like a fraction. Anyway, enough of that. Let's have a look at this example. Right, we're just going to use some Leibniz notation to begin with. For when I differentiate this, right, then I say the derivative. If y equals this function, then the derivative dy on dx equals, well, the 4 comes down, multiplies by the 3, gives me 12x to the power of 3, right? And then a 3 comes down and reduces by 1, so minus 6x squared. Rightio, there you go, Leibniz notation. It's pretty awesome. Now, tangents and normals. Tangent's a straight line that just sort of grazes a curve. Doesn't cut across it, typically. Yes, so just sort of meets it in exactly one point. And a tangent is going to have the same gradient at that point of tangency as the value of the derivative at that point. Okay, same gradient, that's all. Now, to find the equation of a tangent, we need, right, because it's a straight line, two things. We need a point and gradient. Now, to find the gradient, we substitute the x value into the derivative, right? The derivative function, the gradient function. That's what the derivative is. That'll tell us the gradient. And I've got the x value. You'd always be given that. You might have to substitute into the function to get the y value as well, sometimes. Not always. Anyway, once we've got a point and a gradient, we use the point gradient formula. And that gives us the equation of a line. Now, we might express that in gradient intercept form or general form or neither of the above. It doesn't really matter too much unless it's quite specifically mentioned in the question. A good idea, though, to use one or the other. Anyway, a normal is a straight line, a bit like a tangent, but at right angles to a tangent. Okay, so its gradient is significantly different to the gradient of the tangent. In fact, the product of those two gradients will be -1, or we could think of it as the gradient of the tangent, the gradient of the normal compared to the tangent is the negative reciprocal. Right? Change the sign, flip it upside down. Again, I think it's best if we look at this through an example. And I have an example here. So here's a function, y equals x squared plus 3. We know what that looks like. And it looks like this, because we're going to sketch it. That's what we're told to do. It's a parabola, concave up. Y-intercept at 3. Right, the vertex is there as well. Right, yeah, there we go. There's our function. Not too small, because we're going to have to squeeze a whole lot of detail on here as the question progresses. Next up, find the value of y when x equals 2. Right, so substitute into the function. I'm going to label that a. So I substitute x equals 2 into my function. 2 squared plus 3 is 7. Right? Here's my sketch again by the magic of technology. And so what we really did was went across 2. Right? X equals 2. We go up till we hit the curve. we label that point A, and I come across to the y-axis, and that occurs at 7. So the coordinates of A are 2, 7. Right? All well and good. Substitute into the function, find a point on the curve. Now we're asked to find the derivative of our function. So the derivative, 2 comes down the front, I get 2x, the 3 reduces to 0, so that's it, the derivative is 2x. How nice. Now find the equation of the tangent to my function where x equals 2. So it's not just where x equals 2, it's where x equals 2 and y equals 7. We've already determined that. How useful. Now I have a point, I need a gradient, I've got a gradient function, so substitute x equals 2 into our gradient function, into the derivative, and I get the gradient is 4. Now, that means my point is at 2, 7, x1, y1 if you like, 2, 7. The gradient of my tangent is 4, so I'm ready to use the point gradient formula. Y minus y1 equals m into x minus x1. So y minus y1 equals m into x minus x1. If I just expand those brackets, tidy that up a bit, in gradient intercept form, get y equals 4x minus 1. So I found the equation of the tangent. That's the equation of the tangent there. Right, we're ready to move on to the next part. Find the x-intercept of that tangent. Right. To find the x-intercept of any function, you let y equal 0. So if y equals 0, 4x minus 1 equals 0, means that x equals 1/4. I'm going to sketch that tangent on my graph now. So here's my tangent, and you see it just grazes the curve here at the point I labelled A. Right, it has an x-intercept at 1/4. Rightio? And I guess it's got a y-intercept of -1 as well. I haven't labelled that. Right, turns out I don't really need to in this case. Typically you label all your intercepts. This diagram does get a little bit complicated though, so I left it off. Rightio, so there's my tangent. Right, the tangent at A, which is where x equals 2. Righto, next part of this question, find the equation of the normal to our function at, should say, at x equals 2. Calculate its x-intercept and label this C on the sketch. So, we already have the tangent. The gradient of the tangent was 1/4. So that means that, the gradient of my tangent was 4. So that means the gradient of my normal is -1 over that. -1/4. If I multiply those two gradients together, I get -1, which means they're perpendicular. Right angles means if this is the tangent, then that's the normal. So we've got the same point, 2, 7. I've got a gradient now of -1/4. Back to the point gradient formula, y minus y1 equals m into x minus x1. This time I decided because I had a fraction, I'd multiply everything by 4. Gives me this, gets rid of the fraction. And then I think I'm just going to use the general form for this equation. So x plus 4y minus 30 equals 0, just because. Just turned out neatly that time. Anyway, that's the equation of the normal. We also need to calculate the x-intercept and label it on the sketch. So for the x-intercept, y equals 0 means that x minus 30 equals 0, means that x equals 30, right? So my x-intercept is 30, that's point C, and let's draw that on the sketch as well. So here's my function, here's my tangent, now here's my normal. You can see I've indicated it's at right angles here at the point A with coordinates 2, 7. Right, the point B was at 1/4, 0, and the point C is at 30, 0. Okay, they're all labelled now. So you can see here that this actually forms a little right-angled triangle. That may or may not be important later on. But you can see our sketch is getting a little bit busy, but there's my tangent and a normal at that point. We've determined the equation of both of those. Moving along, find the area of the triangle ABC. Area. Now we've got a couple of formulas for working out the area. It's quite possible to make this quite a lot more difficult than it needs to be. So here's my sketch. I've shaded that triangle in, ABC. I want to find the area of that. Now it is a right angle triangle, which means perhaps I could try to find the base and the perpendicular height, AB and AC, one of them being the base and the other being the perpendicular height. I could use the distance formula. That takes quite a long time. It's full of opportunities to make a mistake. Because we've got coordinates, here's a shortcut, right? My base goes from 1/4 to 30, so 30 minus quarter. And my perpendicular height from the x-axis goes up to 7, which reminds me, I've made a mistake in my working. Too late to change it now, but it's going to be too late. You just have to berate me in class, I suppose. Anyway, so the area is half the base times the height. Now that height there shouldn't be 2, it should be 7. Stand well. Right. So half times this times 7 is not 29.75. It's, I don't know, something else. My apologies. You can punch that into your calculator. See the mistake there? Right, I used the 2. I used the x coordinate, not the y coordinate. That triangle there is 7 units high. So the base goes from here to here. The height, perpendicular height, from here to here, from 0 to 7. Right, so correct those things there in your notes. We all make mistakes sometimes. Anyway, that's it. There's quite a lot there, including a howler of an error. Now, let's just go back over what we talked about. Leibniz notation, that's dy dx. It's the same as function prime x. Right, nothing very complicated there. Right, point gradient formula, y minus y1 equals m into x minus x1, is good for finding the equation of a tangent. And the product of a gradient, the gradients of a tangent and a normal is equal to -1. Right, there's that relationship there. If I find the gradient of a tangent, which is easy, we substitute into the derivative to get that. Right, then I can find the normal after having done that. Righto, all of those things and me looking a bit bashful because I got one of the questions wrong. Anyway, that's it for today. I hope you enjoyed. Our next video will be on the chain rule. See you then.